Preparing solutions. A solution with a known concentration is a standard solution. We call this a stock solution. So you'll see if you're reading through a lab, or the pre-lab for a lab, you will see something about requiring X amount of a stock solution. It's used to make diluted solutions for experimental work. Right? When you buy certain chemicals, they will come highly concentrated, and then it'd be up to you to dilute it. Okay. So acids are commonly stored as stock solutions. When preparing a solution for an experiment, a small amount of stock solution is removed and diluted to the desired concentration. So if you have a really, really strong acid, but you don't want it so potent, right, you're going to want to figure out a way to dilute that concentration so it's at a little more reasonable concentration that you need for your experiment. Okay, and you're not going to be working with such, because if you are working with extremely potent acids, okay, you're going to be wanting to work in a fume hood, and obviously we've got this little one here, so we're not going to be able to. So we're going to want to be able to dilute our solutions. Okay, so here's the formula you need to know. Okay, so we've got the volume multiplied by the concentration. So what we have here is we have our stock solution, so whatever we're starting off with, okay, with whatever we're diluting it to. Okay, so this is the diluted form. Now, you're looking at this equation going, okay, wait, this is now a new equation. It's not. We looked at this equation last class. We've seen the following equation. Concentration is equal to the number of moles over the volume in liters. Right? So N moles, volume in liters. Okay, concentration is in moles per liter. A new way of writing moles per liter, right? Because moles per liter is molarity. We actually can use the capital M. So if we have something like 10 moles per liter, we can rewrite this as 10 moles per liter using a capital M. Okay, so we're not going to treat this capital M as molar mass like we were doing in the equation. This is now a unit of measurement. So, now, how does this equation here, C is equal to N over V, relate to the following? Well, what is missing from this equation in both of these? What's missing? What variable is missing in this equation here that's in this? The number of moles, right? Because the number of moles that we have in our stock solution, right? So the number of moles that we have in our stock solution will be equal to the number of moles, okay, in our diluted solution. Okay? So think of it this way. You've got a beaker and you've got whatever your stock solution is. So however many molecules, I guess, that make up the 1 mole of that substance. Okay? And if we want to dilute it, when you want to dilute something, what are you adding to it? You're adding something else that will weaken this solution. So whatever amount we have, we're going to continue to add material to it, but we're not adding the actual stock solution material. We're adding something that will help us dilute it. Okay? We're so-called weakening our solution, but the number of moles is going to be equal, regardless of whether it's the stock solution, so the concentrated form of our solution, or whether we've diluted it. Okay, so that's why the letter N is not in this equation. So we're combining the equation that we've learned already for molarity with this, because we're taking, well, the concentration of our original solution and diluting it, and how much are we going to have of that. Okay. So 2 ways to prepare an aqueous solution with a known concentration. One is to dissolve a measured mass of pure solute in a certain volume of solution. So we're going to take the amount of solute. Remember, the solute is what gets dissolved in a solvent to form the solution. And the other thing is to dilute a solution of known concentration by either adding material to it to try to weaken it to the desired concentration that we want. Using a volumetric flask. A volumetric flask is a pear-shaped glass container. They're used to make standard solutions. So you've seen, okay, you're going to see these type of flasks in which you will prepare your diluted concentration. So step 1, when using a volumetric flask, you must first measure the mass of the pure solute and transfer it to pretty much using a funnel. So you're obviously got a small opening. If you're using a really strong acid, you're not going to want to put it in just and try to get it into the little opening. Right? You're going to obviously use a funnel. Step 2, add the solvent, usually water, to dissolve the solute. Okay, so you're going to carefully add the water to whatever desired amount. So you're going to continue to add the solvent, as we said is usually water, until the bottom of the meniscus appears to touch the line that is etched around the neck of the flask. So if you're trying to create here 1,000 milliliters for your solution, right, there'll be a little line, and here's what we call the meniscus. So remember how we've got like a cohesion that's occurring with the liquid within, that it kind of hugs the walls of our container. Okay, and so we always want to measure to the bottom part of that. Okay. So remember, when a solution is diluted, the volume increases, but the amount of solute remains the same. So we've talked about this previously when we were talking about pretty much the number of moles. So the number of moles remains the same. The concentration, the volume of the concentration might change, okay, when we're trying to dilute a solution, but the number of moles remains the same. So we're weakening it, but we still have the same number of material of our solute within that solution. We're just using something else to try to dilute it, try to weaken the solution. So let's look at our first sample problem. For a class experiment, your teacher asks you to prepare 2.0 liters of 0.10 moles per liter sulfuric acid. This acid is sold as an 18 moles per liter concentrated solution. How much of the concentrated solution should be used to make the new solution with the correct concentration? Okay, so what we have here is the following. We've purchased that high of a concentrated level of the sulfuric acid. We only want, the lab, right, the write-up of the lab says we only want 2 liters of this concentration right here. Look at how diluted we want that concentration to be. Right? A lot stronger. Right? Very many moles per liter of sulfuric acid in this stock solution. So we want to dilute it. So we want to look at our volume and our concentration of our stock system. Then we want to find the volume and the concentration of our diluted version. Our volume is 2.0 liters. Our concentration is 0.10 moles per liter. And as I said, you can write it as 0.10 moles per liter or 0.10 m per moles per liter. So now, what do we have of our stock system? Well, we have the concentration, which is 18 moles per liter, or 18 M. We want to figure out how much volume, so how much of that do we want to take out? That's our X. So we can do it in a couple of ways. We can use the old equation and then kind of manipulate it, or we can just use the equation that I showed at the beginning of the lesson, where it was our V times C of our stock solution is equal to the volume and concentration of our diluted. So once we've got our equation, then we substitute. So the volume, we don't know what that is of our concentrated solution. So we have X. X is being multiplied by the concentration of our stock system, which is 18 moles per liter, equals, what is the volume of our diluted? Okay, the volume, as we have here, 2.0 liters multiplied by our concentration of our diluted, which is 0.10 moles per liter. So we want to isolate for X. To do that, we're going to divide this side by 18 moles per liter, which means what I do on this side, I must do to this side. These divide out, and I'm left with just X is equal to 2.0 liters times 0.10 moles per liter over 18 moles per liter. Notice here, my units cancel out. Look at the units that I have. Remember that when you have volume, your volume must be in liters. Okay, so make sure that you make your adjustments if you are dealing with milliliters. So when you multiply top and bottom and divide by the bottom there, we get 0.011, and what is the and so we know the units are in liters. So we look at the least number of significant digits of my question. What are they? 2. So we just leave it at that. So it then asks how much of the concentrated solution should be used to make the new solution. Well, we're going to want to take out this many liters, but you're not going to want to measure it in liters. You can leave it at that. Your best bet would be to convert it to milliliters. Because milliliters, you'll have a smaller graduated cylinder. It'll be easier for you to convert it. So how many milliliters? Pardon? 11. Next sample problem. What volume of 16.0 moles per liter of nitric acid, HNO3, is needed to prepare 500.0 milliliters of a 2.50 moles per liter of nitric acid solution? Take a moment and work this one out. So we have our stock system, and we have our diluted volume, concentration, volume, concentration. So what is the volume of our stock system? What's the volume of our stock system? Okay, which one's the diluted? Maybe that might be easier. What's the volume of our diluted? The 500.0 milliliters. So what is the concentration that we want it to? 2.50 moles per liter. Okay. Now, what information do we have of our stock system? concentration, which is 16.0 moles per liter, 16.0 moles per liter. What is one step I need to do first? Convert, exactly. I got to convert my milliliters here to liters. So 500.0 milliliters is equal to 0.5 liters. So, least number of significant digits already in my question are 3, right? So ignore the fact that we have 1 there. That's fine, right? In our conversion, we changed it, but it's not gonna. We're not going to use that as the number of significant digits for our answer. So let's use our equation. So our stock system and our diluted. So the volume of our stock system, that's what we're trying to find out. So we have X multiplied by the concentration of our stock system, which is 16.0 moles per liter, equals our volume for our diluted, okay, which is 0.5 liters, the concentration 2.50 moles per liter. The step here to get rid of 16 moles per liter here, so we're going to divide both sides by 16.0 moles per liter, and we're just left with our unknown. So our X is equal to 0.7812, and the volume would be in liters. So now, if we want to, when we're measuring that, that's not really going to be an easy thing to measure. So we're going to have our graduated cylinder, okay, that'll be in milliliters. So we're going to want to, let's say, convert this, and let's say we didn't want to, all right? How many significant digits is that? 3. So we want our answer to 2 significant digits, so it's 0.078 liters. But we're going to change it to milliliters. Is it 3? Yeah, sorry, 3. No, we were right. Ignore that, we were right. So, what is it to the number of milliliters? 0.0781 liters to milliliters. .78 milliliters. How many milliliters are there in 1 liter? 1,000, right? Milliliters. So 1,000 milliliters in 1 liter. Calculate the volume of 18.0 moles per liter of a stock solution that must be used to make 500.0 milliliters of a 0.750 moles per liter of sulfuric acid solution. So we'll separate our stock solution from our diluted. We want our volume, our concentration, volume, concentration. The volume of our stock solution, what is it? We don't know, right? So that's our X. The concentration of our stock solution, 18.0 moles per liter. The volume of our diluted. What is the volume of our diluted?
0.5 liters.
Okay, so you guys have already converted 500.0 milliliters to 0.5 liters. Because remember, if we're using moles per liter, it's moles per liter. We want to make sure our units are also in the same way. So our concentration, we have 0.750 moles per liter. So we have our volume times our concentration of our stock solution equals our volume and concentration of our diluted. So our volume, as we said, is X multiplied by 18.0 moles per liter equals to 0.5 liters times our concentration, which is 0.750 moles per liter. We want to isolate for X, so we're going to divide both sides by 18.0 moles per liter. So what we have is 18.0 moles per liter here, cancel out, and we're just left with X. Moles per liter cancels out with moles per liter, and all I'm left with is liters. So what is the volume that we have of our stock system? 0.02083, and it's in liters. What is it? What are the least number of significant digits in my question? 3. So I want the 208. So it becomes 0.0208 liters. But if you were in the lab, you'd want to convert it to milliliters. How many milliliters is that? 20.8 milliliters. Last sample problem. What volume of 0.25 moles per liter of sodium chloride will precipitate the silver from 50.0 milliliters of 0.10 moles per liter of silver nitrate solution? Our equation, we're combining silver nitrate with sodium chloride. So we're going to have AgNO3 plus NaCl to form NaNO3 plus AgCl. After you've written out your equation, what are you going to do? You want to balance it. Okay. So let me save you that method. It's already balanced. So nice and easy. Right? So what do we have? We have 0.25 moles per liter of sodium chloride. We have 50 milliliters of 0.10 moles per liter of silver nitrate. So if we're using stoichiometry methods, we've got AgNO3, we've got sodium chloride. We know we have moles, we have molecules. So we have how many molecules of each one? Well, we have 1 and 1, right? That's because the balance equation just has the number 1 in front of it. Number of moles of these are what we need to try to find. But with what we're given, we can actually find them. Can I find the number of moles using that? Yes, I can. Remember what the equation was. Concentration is equal to the number of moles over the volume. So if I want to find out the number of moles of silver nitrate, right? I want to isolate for my N. So N is equal to my concentration times my volume. So my concentration is 0.10 moles per liter times, we want to convert 50.0 milliliters to liters, and it's 0.05 liters. When we multiply the two together, we get the number of moles of silver nitrate, which is 0.005 moles. So we have 0.005 moles. We want to find out the number of moles that it will react with, right? How much silver nitrate is going to react with the sodium chloride based on what we have. This is what we have. We're going to be mixing it with this amount. The one thing that they must have in common is what? The number of moles. So their number of moles must be in common. So we have to find the number of moles of our sodium chloride. But because the ratio is 1:1, we don't really have to figure anything out because, as you said, exactly, they're equal. So whatever the number of moles is for this, because it's a 1:1 ratio, is the number of moles of sodium chloride. So we have N of sodium chloride is also equal to 0.005 moles. So the number of moles of silver nitrate that are reacting in this equation is that amount based on this concentration over here. So that many moles of silver nitrate is going to react with this many moles of silver nitrate, but the only thing is, it's got a different concentration. So, we have as follows. We know we have 0.25 moles per liter. So we want to figure out, let me rewrite this in this form, in 1 liter. We have 0.005 moles, but what don't we have? The volume of the silver nitrate that's being used. Right? So that is what we're trying to find. That is our unknown. So we want to rearrange this equation so we can have X up at the top, right? So we're going to bring X over. Yeah.
Is it the silver nitrate or
This of the sodium chloride. Now we're focusing. Because what we've done was we've found the number of moles of sodium chloride. We know that we've got this many moles of silver nitrate that's going to react, and we've tried to figure out how many moles of the sodium chloride we're using. Now we're trying to figure out how much of it, based on this concentration, how many liters are actually going to be used, or how many milliliters are actually going to be used.
no, you kind of said silver nitrate for a second.
Did I say, sorry?
Yeah, but I was kind of
Sorry. So what we're doing is we're switching the x's, because we always want our unknown up in a numerator if we have it in a fraction form. 0.005 moles. We want to bring this 0.25 moles down here, and we're bringing this 1 liter over here, so times 1 liter, which isn't going to really affect anything, but when we divide our units, what is the volume that we're left with? 0.02 liters. So now that 0.02 liters, we want to convert it to milliliters, which comes out to how many milliliters? 20 milliliters. What are the least number of significant digits in my question? 2. So how many do I have, though, in my answer? But how many did I have here? What did we get? Did it come out to 0.02 exact? Yeah. So what do we have to do now? We don't have 2 significant digits. I can do the following. Right? I can do 20 milliliters, right? Because to add a significant digit. But data now goes from 1 significant digit to 3 significant digits. So how do I get that middle scientific notation? So 20 milliliters can be rewritten as 2.0 times 10 to the power of 2 milliliters. Is it 2? No. Sorry. 2.0 times 10 to the power of 1 milliliters. So what volume of this concentration, right? So we're mixing this concentration of sodium chloride with this concentration of silver nitrate. Right? What we're trying to do, right, with what we had, what do we get? We got, let's just look with the hypothetical, without the scientific notation. 20 milliliters, right? So what we've got is, that's the concentration of sodium chloride. So we have our equation, right? Silver nitrate plus sodium chloride to produce whatever we're going to produce. This is the concentration that we've got of that. But we only have 50 milliliters of it. We want to figure out how many, right? What is the volume that we're using of that in our combination? But the thing is, we cannot just compare it and go, okay, well, here's my V, here's my C, what's my V? The reason is, we want to figure out how many moles. We want to make sure we know how many moles. Because before, when we used this formula, what did it mean for both of them? It meant that the number of moles was exactly the same. All right? So whatever number of moles we're getting here is not going to be. We have to figure out the number of moles we're actually using of that. So that's why we have to use stoichiometry. We need to use stoichiometry in order to figure out what are the number of moles of sodium chloride that we're actually going to be using in this solution when we're mixing together that with that. We're comparing two different solutions that we're putting together. In order to do that, we have to figure out the number of moles. So we need to use stoichiometry to figure out the number of moles of silver nitrate, and then using stoichiometry to figure out how many moles really of sodium chloride was used. So we cannot combine, and we cannot really use this equation because we're actually using two separate things. We're not preparing one of these. We're actually combining the two and trying to figure out how many moles of this will be used and how many moles of that will be combined in our solution.